Hi, welcome to the McAuliffe-Shepard Discovery Center and our Superstellar Friday, September 5th, 2025. At the controls, we have Max. Max Stewart is at the controls, so nothing can go wrong.
Good evening, ladies and gentlemen. Good evening. Thanks for being here. Appreciate you coming. If those of you towards the back, you're welcome to stay wherever you like, but there's more room up front. If you would like to come more towards the front, you may. Welcome to our triple header. Actually, it's a quadruple header now, Superstellar Friday nights. Every first Friday night of every month, we have a special presentation, and I'll introduce our speaker in a moment. We have the New Hampshire Astronomical Society with telescopes outside, so don't miss that where there's a break and opportunity to look outside. We have now a new program called Ask the Astronomer. So at the table out in the lobby area, we have an astronomer there who will answer all kinds of questions. Telescopes, like if you have a telescope in your garage, you don't remember how to get it going, or you never got it going, bring it on in, ask questions about what kind of telescope to buy, binoculars, what kind of binoculars to buy, what's going on in the sky. But we have an astronomer here now, whether it's clear or not. The telescopes will only be here if it's clear-ish, but the astronomer will be here regardless of the weather. And then the fourth part is our planetarium show. So when we're finished here, we'll have about a 10-minute-ish break that you can go outside, use the restroom, get some water, and then we'll have a planetarium show about the night sky. And you can think about, is there something that you would like to see or learn about the night sky? I'm like the DJ of the skies, I take requests. So we can do that. So any questions about any of that? Okay, let me introduce to you our speaker, Nathan Schwadron. How did I do?
Usually it's great.
Dr. Nathan Schwadron is with the IMap program, and he is a deputy principal investigator of it. And then also is a lead, as you can see, on the instruments and such. And this is a project that's been in progress for 8 years, and they're getting ready to launch this month. And so he's going to tell you all about it and more. So please welcome Dr. Nathan Schwadron.
All right, well, welcome. So I am delighted today to be here. I will tell you about the IMap mission. It's been, this has been a very surprising journey of my life. I built one of the most, the most complicated instrument I've ever built. I've encountered some of the greatest technical challenges I've ever had in my career. And I cannot believe that we've managed as a team to pull this whole thing together, and that we're launching later this month. So it's really, really exciting. I'll show you some things about the teams of people that have been involved and some of the incredible things that we've gone through. So I want to begin with some really simple stuff, because to me, in going through this thing, it really reignited my own curiosity in a fundamental way. And I wanted to capture that when starting to give public talks about IMap. So this image is the first image of Earth from space. This is 1946. Now, when I think about this type of thing, I look at this and think, okay, 1946. By 1960, we were sending people to the moon. Think about that. I mean, 15 years. Go back 15 years now. You know, I mean, the transformation of our society into the space age was unbelievable. The other thing that to me as a scientist, when I see this image, what that does to me is it makes me realize that we fundamentally, that image changed the way that we think about us here on this planet and our relationship with what's out there. Nowadays, we have all sorts of images of Earth from space, and it's easy to think about. But before that image came through, we had no way of thinking about what we look like here back on this planet. It's a really peculiar circumstance. There's actually sketches done in the 1800s of what people thought Earth might look like. And of course, certain things were completely out of proportion. They didn't think about the atmosphere. They didn't think about the types of things that we actually deal with. And of course, the experience of astronauts going into space is incredible because they suddenly realize that they're leaving all of humanity behind. They're alone in this void. And back there is teeming with life on Earth in this very peculiar situation. That's the opening. That opens up our view, this window into the universe, and starts to really lead to some profound questions. Okay. The big one that leaps out to me is what's beyond. When we see an image like that looking beyond, we suddenly think, wait a second, where are we within the universe? What creates the conditions that give us an Earth that's teeming with life? And what are we going to encounter in the future as we go out there? Now, this is a kind of a silly image. It's just a big round thing. This is actually what we call a full sky projection. So it shows all 360 degrees going all the way up from north and south. So anybody guess what these two things are? V1 and V2. The Voyagers, Voyager 1 and Voyager 2. And does anybody know, you can answer, why today is such a special day? It's Voyager 1's birthday today. Voyager 1 turned 48 years old. 48 years. It was launched in September 5th, 1977. And if you think about what I just said, the first image of space, of Earth from space, that was 1946. So we're talking like 31 years later, and suddenly we're in the midst of the space age. We launched Voyager 1 and Voyager 2. Voyager 2 was launched earlier in the same year of 1977, just in August. 2 years later, they're at Jupiter. Another year later, Saturn. And in 2012, Voyager 1 was the first human-made object to leave the sphere of influence of the sun, to leave our solar system and enter the galaxy. Incredible that this has happened, to me, that this has happened in our lifetime. Remember that image? That, in 2009, is the first image of the boundaries that surround our solar system, that separate us sitting in Earth and within the solar system from the medium of the galaxy. That's the medium, that's the precipice that Voyager moved through. The structures here, I'll talk about some of these a little bit today, were never observed before. When we first made this map of what we call our heliosphere, sun, sphere, the sphere around the sun is actually not spherical at all. That notion, what we call the heliosphere, didn't even exist 60 years ago. So the question of what is beyond is fundamental here. Just like the first image of Earth, this gives us our first snapshot of taking the leap into the galaxy.
Is that from IMap?
That's from IMap, the Interstellar Boundary Explorer. Exactly. Now, we as scientists got very excited because one of the things we got to get the cover of Science. This was from the cover of Science in 2009. And so it was very prestigious, and the first image and painted it on a picture of our heliopause, and you could see these weird lines. These are actually magnetic field lines from the interstellar medium. Travel around our whole heliosphere. Now, we as scientists, we make images like this, and we get people saying, oh, that's cool. But at least if I'm in your shoes, I would say, okay, that's nice, but who cares, first of all? And second of all, what's that image even of? In order to make that picture, we had to look in very, very different ways. And that is a fundamental theme of this talk, is looking with new eyes and seeing in new ways to be able to see the boundaries that protect us. These boundaries are fundamental for creating conditions throughout our entire solar system that have allowed for life to develop here on Earth. And they're changing. And they're changing very quickly. Now, this is kind of, to me, it's a very important image. Some people think it's completely goofy. The quote, l'essentiel est invisible pour les yeux. The essential is invisible to the eyes. And actually, the quote before it, I think, is equally important. It is only with the heart that we see rightly. We are in this curious circumstance. We are here as a society. We are here as a civilization. We are here as a culture, a world culture, an emerging world culture. And we're on the precipice of discovering what's out in the galaxy. We are like children realizing that we must grow to evolve. What are the conditions that keep this planet working? And how will it change in the future? To answer those questions, we have to learn to see differently. We have to learn to see the boundaries that protect us, and we have to learn how to penetrate them. That's equally, it's important for us as we emerge technologically. We put all this equipment into space. It allows us to use cell phones. It allows a whole bunch of technologies to emerge. Everything from mining to communications depends on the use of space. And we have to learn to navigate it as we think about human exploration too. One of the big problems that we encounter, we want to send a human to Mars, or send a human to the moon for long periods of time, or even just to take human beings and put them on very high altitude flights. We have to deal with the problems of radiation. Radiation is much worse in space than it is here on the planet. We're protected by the planet's atmosphere, by its magnetic fields. And it's much worse in the galactic medium. So these boundaries that surround our entire heliosphere actually protect us, the entire solar system, from a radiation environment which probably would have precluded even the development of life. We are, for the first time, seeing the cocoon that's allowed us to develop. Now, the other thing that I wanted to point out here is something that I really value and I've come to talk about more and more. It's this other line. It is only with the heart that we can see rightly. To me, that is curiosity. That is the curiosity that we have as a child that drives us forward. It is the curiosity that, at least for me, and the many times that I wanted to give up in building this very complicated instrument and dealing with all of the challenges that we had, made me move forward because I was curious. I wanted to know the answers to the fundamental questions about why we are, where we are, what the conditions in the galactic medium really are. Those fundamentally drove us. And they drive us as a society. They are driving us towards a better understanding of space, a better understanding of our relationship with the cosmos, and the search for life elsewhere. They're also forcing us to have and ask what our future is within the cosmos. Now, one of the interesting technical details about this mission, we're launching no earlier than September 3rd, 23rd. That's what I'm supposed to say, but we're probably going to launch around it. And guess what? We're launching on SpaceX rocket on Falcon 9. The rate of launches has been a huge technological advancement. And it comes exactly from this, from our curiosity, our desire to push the limits, and our desire to emerge, to advance, and to adapt. In some cases, we do things that are nuts and they don't work out. We learn from those and we move on. In other cases, we take the step forward. This mission is an example of that. It's this incredible collaboration amongst a group of people, all with a common desire to take the next step to advance human knowledge. And at the end, to a person, if you ask the people on the IMap team why they're doing this, they're not going to tell you money. They're not going to tell you prestige. They're going to tell you, we are doing this to advance human knowledge. That's why we love what we do. It's an incredible, incredible activity. Now, this is a picture that we can only draw. We cannot image our own galaxy. But we have an idea that we are living somewhere out on the spiral end of our galaxy, away from the center. And us, all that we call is home is right here, in this tiny little neighborhood. And what's going on there is we have a bunch of what we call clouds. This is called the local interstellar cloud. There's a G cloud, there's a blue cloud, there's a bunch of these little clouds that various people have named. And it turns out that we're right on the edge of what we call the local interstellar cloud. In the next 10,000 years or so, we likely will be moving beyond that. And it means, because not only are we on the edge of this cloud, but these clouds are colliding. They were generated partly from a supernova that happened about 10 million years ago. The conditions throughout our heliosphere are going to change as a result of these conditions changing. Again, it forces us to ask fundamental questions about where we're headed, how the conditions here were created to begin with, and what's going to happen next. We don't know that answer. Now, within that medium, let me just go back one slide. This is our sun and our solar system sitting right at that edge of the cloud. We are moving through that medium, and if we move through that medium, we are like on a boat. So when you sit on a boat and look out, you see the bow lift in front of the boat. You see all the material that gets pushed around the sides. And then there's sort of a turbulent wake behind. That's exactly the condition of our heliosphere. The sun produces the solar wind. So inside what's called the termination shock, it does a really good job of inflating that solar wind inflates this nice bubble where all the planets are. And so the solar wind comes out and eventually it rams into the interstellar medium. This is, and the pressure is dropping as it moves out. And eventually it creates a structure. This is called the nose of the heliosphere. That's the front part of the heliosphere. And this is where all that interstellar material gets pushed out. This is the portion that Voyager 1 moved through to become the first human object to move into galactic space. Just a few years ago, in my lifetime, we knew next to nothing about this. And now we are starting to learn about the interstellar medium that we are moving through. It's an incredible time, and it has incredible implications for the environment in which all of life formed. We are the only case history we know of life developing within the universe. I hope that we, within our lifetimes, will discover more. So far, we're it, which is also sort of incredible and leads to some pretty profound questions. There's our nose. I like to put this, a lot of times I show these pictures and they show the nose, and everybody's like, what are you talking about? What's the nose? The nose is the direction of the boat, the direction that we're moving through this medium. So that's our introduction. And now I want to show you just some images that will show you some of the things that we deal with. These are the local interstellar clouds that we're moving through. And as we focus in here, we will get closer and closer and see the sun and the heliosphere moving through this medium. I apologize for the orientation suddenly shifting on you, but this is the motion of the sun moving through this medium, creating the bow wave in front, the heliopause between, and the structure of our heliosphere in the middle.
I'm so sorry to relate, first of all, because we could have answered this question, but are you saying that as the solar system, as the planets revolve around the sun, we're kind of still moving through space, almost in like a corkscrew sort of shape, and that that nose part is the part that is kind of in front of that, or
Yeah.
behind it?
It's the part that's in front. So if you take a look at this image, this is the sun and the planets. These guys are all moving through this, but this whole thing is moving as a whole through the medium, pushing its way through this interstellar medium and creating these very compact molecules that surround our entire heliosphere. Did I answer your question?
I believe so.
Yeah, yeah,
May I ask?
please, yeah.
So I can remember, teaching a class that it was the moment in time, the day, the era, when Voyager 1 entered its heliopause. And so I have two questions. One of the ones was that they didn't know how big the heliopause was, how long it would be in there, hours, weeks, years. And then so my other question, seeing this now, what direction did it go to the heliopause, and then how thick was the heliopause after all, finding the story?
Yeah, it's kind of an amazing story, but let me just tell the slightly longer version of that. When I was a graduate student, we had Voyager 1 was still inside that whole structure. And every year, the scientists would come up with a new estimate for where this terminal was. It was always about 5 astronomical units beyond where Voyager actually was. As it would go out, they'd say, well, maybe it's a little further. Now we have better calculations, so we think it's just 5 AU. We're almost there, we're getting there. We finally crossed. And then a few years later, Voyager 1, which in this picture was moving out like this, so slightly north, Voyager 2 was moving slightly south. It crossed the heliopause. This is the separation between our solar wind and the interstellar medium. And at that point, when it crossed the heliopause, there was a huge debate. Scientists, some were saying, we have not crossed the heliopause. We're still in this bubble that's associated with the heliosphere. Other people were saying, no, we've crossed, and the conditions of the interstellar medium are completely different than we thought. All the signatures that we predicted that we would see when it crossed were completely wrong. So it was a really, really interesting time. Now, this structure is about 10 to 15 astronomical units wide. So about 10 to 15 times the sun, but it's not always the same. Sometimes it's thicker, sometimes it's thinner. And it changes in response both to what the sun and the solar wind are producing, but it also changes in response to what this interstellar medium is doing. The physics of this, which I could spend years talking to you about, is completely different than we thought. There's all these competing forces, some of which we accounted for, but others that we didn't. And so the complexity of this is just something that we're beginning to understand. And those debates, which just started at that time, continue. That's one of the things that's motivated us to create the IMap mission. Yeah, Dave.
This is bringing back memories of things that I learned a while ago, but I would like to bounce off to you to see if it's still what is, because as you said, things change.
Yes.
And the ideas change. So I was in the understanding that the heliopause is like the place or the boundary where the influence of the interstellar medium is now greater than the influence of the solar wind.
Yes.
Is that true?
From a pressure standpoint, that's right.
Yeah, okay.
So what's happening here is that this whole solar wind is expanding in 3 dimensions.
Yeah.
So imagine that you're trying to blow up a balloon. That's what the sun is doing with this whole thing. So the bigger that balloon gets, the less and less pressure is actually carried, right? Because you're expanding in volume. As you expand to larger and larger volume, the pressure drops. So eventually you're going to get to a point where you can't expand anymore because the domain outside of you is pushing back so hard that it can't expand anymore. And that is what defines the termination shock and eventually the heliopause. So when you get beyond the heliopause, the pressure within this medium becomes, essentially comparable right at this boundary. But then the solar wind can't make it anymore, because if it were to go out further in volume, the pressure would drop and the interstellar medium would win. So that is the place where the interstellar pressure dominates.
Good.
So then, how thick was the heliopause? How long was it in there before?
Yeah, it was about, I think it was about 12 to 15 astronomical units, and Voyager 1 goes about 3 astronomical units per year. So I think it spent about 5 years in the heliopause. Yeah. Okay. Any questions, guys? Now, remember what I was talking to you about these questions about looking at other cosmos, through the cosmos and thinking about the existence of life throughout the cosmos. That's one of the biggest questions we have right now in astronomy and physics that drives us. We're looking for extrasolar planets. We're looking for the conditions that support life elsewhere. So the same heliosphere that we have exists around other stars. This is a star in Orionis, so this is an encapsulation of Orion. This is BZ Cam. BZ Cam is in Camelophylax, which is the giraffe. It's a cataclysmic variable star. It's 2,500 light years away. This last one, Mira, very beautiful. It looks like a comet. This is imaged in the UV by the Galax spacecraft. It's only 300 light years away. It's pretty close. And it's in Cetus. It's in the whale. That's sort of near Pisces and Taurus. So these are just examples. The reality is that every single star has a solar wind. Every single star produces a heliosphere that's like this. And depending on the portion of the interstellar medium that they're going through, some of these emissions are very, very light, very close to the star. Those are going to be very harsh environments. Some of them are harder to see, are weaker, and those are more like what we have here in a heliosphere. But this is a big fundamental part of what creates the conditions for life to form if it does exist in any of these locations. So how does the sun work? How does it produce this heliosphere? This shows a particle in the solar wind going out as it inflates. This is the heliopause. And this is that particle going out to the heliopause. Now, I'm going to come back to this, but one of the things that, there a question? Yeah. So most of the stuff that comes out of the solar wind is just good old protons. So take a hydrogen atom, remove an electron, you've got a charged particle that goes out and creates that, inflates that medium. Now, I told you that we are imaging the structure, we created the first image. And the question is, how does that work? How do we create this image? What I'm going to show is a little movie, and it shows these protons that seem to be gyrating around or something. What they're gyrating around is a magnetic field. So if you have a magnetic field and you take a proton, it's going to gyrate around that structure. Eventually, it will collide. If it collides with a hydrogen atom, it can actually itself become a neutral particle. And at that point, it does something really important. Whoops. This is the movie I was having trouble with. Okay, so this is our gyrating proton. It's gyrating about its magnetic field. Bam! Collides. Now it becomes what's called an energetic neutral atom. It's neutral, has no charge, so it can move back in the straight line back through the solar system. Back to Earth. And eventually, if we're lucky, it moves into one of our instruments. It's those neutral particles, those hydrogen atoms, that we use to image these structures. It's really remarkable. And this is the part where we're able to see with new eyes. These new eyes are the instruments on this probe. This little guy is IMap. It's called IMap low. That does the low energy portion. I'll pass this around. This is one IMap high sensor, so a little bit higher energy neutral atoms. Both here and here, there are different angles so they can image different parts of the heliosphere. You have ultra that goes to very high energy, so that's this one down here and this one down here. And then I'll talk a little bit about some of these other instruments. But as I talk about this, I can pass this around. This is really fun. This is a 3D printing of IMap that Princeton produced. These are the solar panels that are sitting on the top. Dust instruments here. You have solar wind instrument here. A lower energy imager particle instrument here. It's called CODIS. The HIT instrument. And these are all beautiful instruments. And then not to forget about the electron instruments. Tiny little electron instrument sitting on the side. Pass this away. Very cool 3D printing. And this is the image of neutral atoms that we see for the very first time of space, and this comes from McAuliffe. Now, I was telling you that this medium that we must now navigate, we want to send satellites into space, turns out is a very violent medium. And you have what are called coronal mass ejections. This is called the coronal mass ejection, which sweeps out. They create strong compressions and shocks. They accelerate particles to some of the highest energies that we know of. And they create the harsh radiation conditions that we have in space. If you're an astronaut and you go to space, this is stuff that you worry about. And I'll tell you about Bill Anders, an astronaut. So a number of years ago, I worked on the crater instrument. You can see exhibits here of the crater instrument. That's on LRO, the Lunar Reconnaissance Observatory. And we were studying radiation in space because we were interested in getting astronauts back to the moon. And so one of the things that I did back in the day is I used to study models of radiation and how they would go through human tissue and what type of dose they would create in human tissue. It was fundamental in understanding the health of astronauts and anyone who was in space. So I was sitting there at lunch one day in a conference, and a guy came up to me and sat down and sort of talked a little bit. I said, "Oh, hi, I'm Nathan." He says, "Oh, hi, I'm Bill." And I said, "Bill, nice to meet you, Bill." And then I ate a little bit, and he said, "Do you know who I am?" And I said, "I have no idea." He said, "I'm Bill Anders." He was the first astronaut to circumnavigate the moon. And he said, "You know what? When I was an astronaut, you radiation guys really ticked me off." And I said, "Why? You know, we're trying to protect you guys." And he says, "You have no idea what it's like to be in space. You're trying to operate in space, and you know that there's something going on all the time, that whether you like it or not, whether you're sleeping or awake, but it's damaging your body and you know nothing about it. You guys were constantly talking as if it was interesting and it's, you know, a major threat when they're in space." So when I was grounded, you guys became my best friend. Because now I'm no longer worried about it. I'm interested in protecting my other friend astronauts. So Bill passed away a few years ago. He was 92 or 93. And you would think that Bill died of old age. He did not. He went down in a plane because Bill was an explorer, and he was to the very, very end. He was a good, good friend and an incredible guy.
Did he take that first picture?
No.
Well, that was the-
No, that was that was before his time, or he was like pretty young at that time. So here we go. We're about to launch IMap into space, and this shows the launch. And we're going to what's called the Lagrangian point, Lagrangian 1. It's a point between Earth and space where gravity is balanced just right in space. There's nothing here. But because it's a gravitational point that balances the gravity of the sun and the gravity of Earth, it's actually a point of space, a spacecraft can orbit between the Earth and the sun. I know, it's unbelievable, it's mind-blowing. Absolutely incredible. We have a bunch of satellites that are there. It's so weird that they're just orbiting this like blank spot in gravity.
There's something there. We may not be able to see it, but it's there.
That's right, exactly. Seeing with new eyes. And we are about to do this. And for me, as you look at these instruments, you can imagine the human hours that go into these things. Some of us working 24/7, many weeks. It was an incredible thing. Yes.
What did you notice about the materials? That's basically a space camera, right?
Yes, yeah.
Is how lightweight it was. Like, I expected it to be a lot heavier, but it was felt so lightweight. It makes perfect sense why things would be made to make it as lightweight as possible.
Oh, yeah, yeah. Big
That
time.
really stood out for me.
Every kilogram costs you about $1 million to get in space. Every single kilogram. Wow. Yeah, it's a big deal. So this is it. We're about to take that entire pile of things that we have got in clean room suits. I mean, when I go and interact with the spacecraft these days, going to Florida, I've spent so much time in Florida in the last few months. Just there with the spacecraft. We just did our spin balance test. But I go into the clean room and a very sick feeling comes over me. You look at these instruments as we take off the covers and we run these tests, and you think the amount of human labor and work that went into making this thing is just incredible. And there you are with these instruments. If you trip, if something happens, if there's a discharge and you damage one of these instruments, that instrument will never work in space. And so it is just, it's It's mind-boggling. And we're about to take that whole thing, put the entire spacecraft into our launch vehicle, together with two other spacecrafts, SWIFO and Carothers, which are both studying different parts of solar activity, or the effects of solar activity. We're going to put it in this spacecraft, Falcon 9, and launch it. All of the risk is right there. Getting off the launch pad. There's some ridiculous percentage that I don't want to think about, which is the risk that you're not going to make it to space. And that's the endeavor we do. So this is coming up no earlier than September 23rd. But you can certainly view it on NASA TV, or you can come down and go to Florida and see it for yourself. There's lots of places to see it on Cocoa Beach. Or you can go to nasa.gov/live and observe the launch. So it's going to be around that period. And you can imagine that I'm going to be very nervous. So this is our spacecraft. This is the magnetometer that's sitting out. There's my instrument, IMap low, IMap high, IMap high, ultra. There's the swapping instrument, IDEX, which measures dust. Incredible payload. 10 instruments. Another picture of this. You can see the door. This is the door that protects the dust instrument that we open. This magnetometer boom starts stowed, and then once you get into space, we release it and it extends out. This little instrument is done by a friend of mine, Blue Stove. Very small instrument, but very important. Measures electrons coming out. Incredible set of instruments. So we go to this point, the Lagrangian point I was telling you about, this weird gravitational point that balances the sun and the Earth. We're 1 million miles from Earth, 98 million miles from the sun. And then this thing rotates with its spin axis towards the sun. And what we're showing is two fields of view of the IMap high instrument looking at the neutral atoms. And so these fields of view rotate around and they create cones, and over the course of 6 months, they sweep out the map of the heliosphere. So there's that process of rotating, sweeping out the maps of the heliosphere, and this shows the image that you then build up of the heliosphere in these neutral atoms to try to understand this precipice, this boundary between the solar wind and the interstellar medium. These are our 10 instruments. SWAPI, which measures energetic particles, and solar wind, POTUS, higher energy particles, HIT, the highest energy particles. So this is actually the closest to actual radiation. The magnetic fields of the solar wind, the electrons of the solar wind. So this first part is all the instruments that measure space weather. So these are the things that are going to become the next great gateway to understanding the space weather that affects all the technologies here on Earth. It's these instruments that are going to give us the data that can give us warnings for space weather and can allow us to protect astronauts and humans in space. We have the IMap low instrument, which measures low energy neutral atoms, IMap high, higher energies, and ultra, the highest energy energetic neutral atoms in the medium. The dust instrument, which measures interstellar material and material in our solar neighborhood. And the glows instrument, which is going to measure a UV glow produced by the same interaction with our interstellar medium. And this shows the locations of the instruments. So one of the things that you'll see if you guys go through, there's a bunch of videos. You can see some of the team members that are actually interviewed. One thing that we all know is that this instrument and the spacecraft would not exist if it weren't for the dedication of this incredible team. And this is the whole team that's come together. We have 25 institutions. We've all collected at APL, which is in Maryland. Just an amazing group of scientists and engineers, educators, staff people who all endeavored to make this thing happen. One thing I just wanted to throw up is some of the pictures from my team, the IMap team. This is just one of the teams put together. These are all the people that helped put together the IMap instrument. And this involved people from APL, people from Southwest Research Institute, Princeton, University of New Hampshire, Sierra Space, which built the pivot platform that we rotate on, and Princeton University. And one thing that you'll see with all these people is this sort of, everyone's giving their thumbs up. And it's because we're all pushing through these incredible things. We're saying thumbs up, we're going to make this thing work. This is our actual instrument, a few pictures of the instrument off of the spacecraft. This is when we were weighing the payload. You have a collimator out front that collimates the particles. And then, I won't go through all the details, but a bunch of things to first create ions, and then bend the ions, measure their energies, and measure their actual composition through carbon flows that we made right here at University of New Hampshire. This is incredible exercise in putting all this together. These are some of the measurements we took at Princeton University. This is Mitchell Shen, who's the deputy lead on the instrument. This is our team. They were working many long days. You can see some very tired people. There's Fatima, she's very tired. People were not happy at this time, but people were working through it and figuring it out. And this is the instrument in the calibration chamber. And there we are at Princeton. This is the last day, end of calibration. We put IMap in its box, put it on the truck, and sent it to APL for integration with the spacecraft. Later, the spacecraft was all moved together with all the instruments down to Florida. It's at Astrotech right now. It's about to be put into the launch vehicle and onto the Falcon 9. So it's that was a pretty incredible event. All this started with IBEX, the Interstellar Boundary Explorer. Small Explorer mission, smallest mission that NASA ever does. We put it up, people didn't think that the mission would work. And for the first time, we made an image, the boundaries of a heliosphere. And at this point, we're actually discovering and mapping the conditions of a heliosphere and understanding the origins of space weather. So, thank you. Without answers. Thank you.
Questions? Avez-vous questions?
Actually about Voyager, when it got beyond the heliosphere, what did you find?
So we're still in this medium. So one of the things that we thought is naive is that Voyager would go into this interstellar medium and we see a steady magnetic field, we'd see calm conditions, everything would be normal. And instead, what we saw was all sorts of disturbances, large-scale disturbances that were within that medium. So what that told us is that the medium that's within our galaxy is much more disturbed than we ever thought. It's not this ambient medium. It's a medium that's filled with interactions between the plasma and the magnetic fields and the interject particles. They all end up contributing to creating multiple structures within that medium. Some of it is coming from our heliosphere itself, but some of it are actually intrinsic to the medium. Now, there are a bunch of discoveries that we made as part of IBEX. Just as an example, we discovered that the direction of the interstellar magnetic field, this magnetic field that's around our heliosphere, we were able to link that magnetic field with what we are seeing with IBEX, with what very, very high energy cosmic rays, TeV cosmic rays, those are 10 to the 12 EV cosmic rays that move all the way through the galaxy. are directed by those magnetic fields. And the fields that we are measuring lined up with those magnetic fields, explaining a paradox that we've had for over 100 years in the structure of cosmic rays around our heliosphere. So what we're learning is what this medium is. We're starting to understand the nature of that environment, the clouds that structure that environment, and how the conditions in our whole heliosphere are regulated as these boundaries are formed. That's kind of an example of some of the things that we're learning within the medium. Right now, there's more controversies than there are solutions, because the scientists are arguing and having different ideas about what this medium is actually like. We're just discovering it for the very, very first time. So it's kind of like when we sent the first probes into space, we had to discover the space environment. We had to understand the solar wind. Even the nature of the solar wind, people didn't believe when it was first discovered. And that's kind of the same type of thing that we're dealing with right now. It's trying to discover sort of the underpinnings, the foundation of what is the interstellar medium that we're moving through.
So my question is very similar in that if you have all these stars and they're moving and they all have a heliosphere, but their influence stops at the heliosphere, where are all these other particles, interstellar particles and energy all coming from? If it's not coming from each individual star, where are they coming from and how are they moving around and impacting the heliospheres of all the stars?
Great question. So there is the nature of the interstellar medium. First of all, I view it as a cosmic junkyard. It's the stuff that's left over. It's the stuff that's left over from the Big Bang. It's the stuff that's left over from the winds that travel out. It's every time a star goes supernova, it blows out its material and it enriches the interstellar medium. It's the stuff that's left over from the formation of other solar systems. The reason I say other solar systems is because the material that we left behind is somewhere else by now. We have moved around the center of the galaxy many, many times in the existence of our Earth and of the solar system. So it is all the material that gets processed. And what happens over time within that interstellar medium is it gets richer and richer in heavier material, because stars are processing material, making heavier and heavier atoms. And so there is a process that's called galactic nucleosynthesis. And it means the enrichment of matter. So in fact, one of the measurements that we take on my instrument, IMap low, is measurements of deuterium, very similar to hydrogen, but different, with 3 neutrons. And, three neutrons. Deuterium is the ratio of deuterium to hydrogen, gives us an atomic clock for the origin of the Big Bang, or essentially the origin, the amount of time that the universe has been around. And so that's another fundamental measurement. We've never made it directly with matter from the interstellar medium. We've always had to look far, many light years away, to make those types of measurements. So that just gives you a flavor of the types of things that exist within that medium that we really know nothing about, that we're just at the tip of the iceberg of understanding. And again, I view this as a time in which we as a species are actually moving out. We're starting to ask these fundamental questions about our own existence here on Earth and our relationship with the universe and with the galaxy. And this is that type of mission, which is going to give us those next set of questions that's going to propel us beyond. Questions? Yeah.
So I saw in the listed instruments, there was a whole lot of stuff about things like electrons, these neutral protons you were talking about, UV radiation, that kind of stuff. But is there any information we could take from all of those instruments to gain more insight about things like neutrinos or other types of particles that aren't really mentioned up there? And if so, what do you think that can kind of point us to in studying the heliosphere?
So the medium of the heliosphere it's a system. It's what we're learning about the sun and how it produces the solar wind is that it is an evolving system and all the pieces are linked together. The magnetic fields are related to the solar wind. The solar wind, the nature of the solar wind relates to the disturbances, the coronal mass ejections that come out. We don't measure neutrinos. Neutrinos are actually measured, closer on the ground typically. So we're not going to address the solar neutrino problem, but we do address what creates the hot corona, what creates the solar wind, what creates the conditions and the space weather that affect future explorers in space. And it's understanding that system that requires all these measurements of different parts of the system. The electrons, the solar wind, the particles like pickup ions that are within the solar wind. All of these particles contribute to create energetic particles. That's the system picture that we have to develop with this mission in order to be successful.
So, sorry, to piggyback off your question, I'm sorry to interrupt. So is ions, is measuring ionic activity part of this project specifically more than maybe, the neutrino, for example?
Absolutely, yeah. We measure remember when I was showing the payload, I had two lines here, two rows. Yeah. So this first row is what's called the in situ payload. That's measuring the magnetic fields, the solar wind electrons, the solar wind particles, and then all the spectrum of energetic ions that are within that medium. And we're trying to understand the origins of particle acceleration, how particles are accelerated, not only in our space environment, throughout the galaxy and throughout the universe.
That's a big quantum question right now.
Oh, yeah, big time, absolutely. So these are the particles, these are the space weather particles. These are the things that are really going to answer those fundamental questions. Whereas these guys are looking out. They're looking out at the conditions in the interstellar medium. And if you look at the whole picture that you have here, you have a payload that's designed to understand the system as a whole. And that's why this mission is so ambitious, is putting all these pieces together. Yeah.
When you use words like outside of the heliosphere is a junkyard and there's parts and there's leftover, is the suggestion then that within the heliosphere of each of the stars is an organized system as opposed to a disorganized system outside the heliosphere?
That's absolutely right. Yeah. If you take a look at this picture. There we go. This is the solar wind that's produced by our sun. It's constantly blowing out material and organizing the system. So that's the thing that creates the organization within these stars. We're living literally, to some extent, in the solar wind, the extension of the solar atmosphere. Outside, in the interstellar medium, you have all these clouds that are running into each other. You have the remnants of the Big Bang, you have the spiral arm, the structure that exists there. It's all these pieces that are colliding. They may be partially mixing. That's a medium which has a lot less order than the stellar winds that are created by the stars.
Round of applause. Hang around for a few minutes if people wanted to ask some questions up close and personal. We're gonna take about a 10-minute, 12-minute break. So you can check outside. I don't know what the clarity is, but check outside. There may be some telescopes out there. Ask an astronomer, use the restroom, get a drink of water. And about 12 after 8, we'll start to gather at the planetarium theater entrance. And we'll have the doors open by 8:15. And we'll have a show about the night sky, what's going on, and entertain your questions about what you would like to know, see, and learn about in the night sky. Sound good? Okay, thank you, and again, come up and chat with Nathan if you would like to. Yes, thank you.